start. If you can see my screen. Do you see my screen?
Yeah.
Yeah,
Fine.
please.
So we, the previous lecture we obtained the expression for Riemann curvature tensor, which is very important. And we discovered that the Riemann tensor appeared due to the fact that covariant derivative operation is not commutative. And again, we understand why, because as you can see from this picture, so we can see that when we go around the closed contour, the vector will not come back in the same position and with the same orientation. So this tells us exactly the information about curvature of the space. I also could see that some of you send me home tasks, so I will look at this careful later. Now we will continue, and just a second. Okay, now we the title of the lecture. So this is a property of curvature tensor. Here let's write. Properties, so it's not one of. So, and we will discover we'll discover now the property of curvature tensor, which for us also will be important. And the first one, so let's start. So what we know, okay, we'll also repeat that, and we will work with a covariant Riemann tensor. So it means that we, for example, have we have for example tensor, mixed tensor. So one, I'll write like this: AKLM equal. So if we have a tensor with mixed tensor, here N, here KLM, we can apply bimetric tensor IM. So in this case, we have fully covariant curvature tensor. What is also important that since we could see that Riemann tensor can be expressed through the Christoffel symbols, where it is here, okay. So we also know that Christoffel symbols they can be expressed through metric tensor. In principle, we understand that the curvature tensor also can be expressed through the metric tensor. This procedure, needs some time to obtain. So, and I don't want to spend time for this. I will write you the final expression, which you can use to obtain the properties of curvature tensor. But if you would like to understand how we can obtain it, so just write me and I can send you my this proof. So I just will write the final result. So this you can write in your conspect, that expression of Riemann tensor through The metric tensor is in such a way. So we have R I K L M, which is equal 1.5, and we understand why this appeared. It's maybe appeared due to the fact that the Christoffel symbols has a summand multiplier. After this, we have G I M. There is also even a mnemonic rule, but you can invent your mnemonic rule, and it's not a point to remember this by heart, so I will not ask this expression to write it on exam. So I am after this the just, as I say, normal derivative. So I just put here comma K comma L. Again, I will remind that this comma, it means that I need to write like this. Okay, so this is what it means. Plus GKL I M minus GIL KM minus GKM IL. So you can see that we have such a kind of permutation of the indexes with some rule. This I can kill. Plus, it's not all, plus JNP gamma, and this is structure gamma minus gamma, gamma. And again, we can distribute indexes. So here we will have N, here we will have P, and here KL, here IM. So here again, we will have N, here P, and here KM, IL. So this is expression for the Riemann tensor through the metric tensor. And now you can see that it's not a simple business to obtain it. So why I don't want to spend the time for this. But if we have it, we can in principle immediately understand that some properties of the curvature tensor. I would like to see how many people we have. Okay. So the first one, this is the property that curvature tensor is symmetrical to the permutation by pair of the indexes. What it means? It means that if we have tensor Ri with indexes I, K, L, M, and we, for example, we choose here this pair, okay? So, and if we will change the places of this pair of the indexes, so in this case, we will have the same tensor. So it equal LM IK. Here it's very important to be careful with the indexes of the tensor. So you can see here that there is a various rule how we can, when we change the places of the indexes in front of the tensor. So to see it, it's very simple to see it. So if you will write this expression for this case, for this case, you will see that it will be the same. Okay. The second one, this is property that, of course, you will see it also taken into account that the Christoffel symbols are symmetrical respect to the change of the indexes which are in the bottom. So we also need to take into account that, for example, gamma pik equal gamma pki. And in this case, you really can see it. Okay, the second one, this is the property that the Riemann tensor is antisymmetric with respect to the permutation of the indexes. I might say I can write R, and I will put index 1, 2, 3, 4. With respect to permutation of indexes 1 and 2 and 3, 4. Like this. So antisymmetric. Antisymmetric, it means that the sign in front of the tensor will be changed. Let's write it. It means that if we have R, I, K, L, M, and for example, I will choose these two first indexes. So it means that if I'll make some permutation of these indexes, I will have minus R, K, I, L, M. If I will again do this, choose, for example, this, I will see of these two indexes. Minus or minus will give us plus, so I will have R, K, I, M, L. So this is the general rule, which also can be seen if we will use this expression of the Riemann tensor through the metric tensor and Christoffel symbols. The third one, third property, this is, it tells us that if we have a cyclic permutation on the for some chosen sort any indexes, the sum of the result tensors will be 0. So I will write it using formula. So if I have R, I, K, L, M, and for example, I will choose these 3 indexes. Okay. And after this, I make the cyclic permutation of inside, of these 3 indexes. So it means that I need to write plus R, I keep, and after this you write M, K, L, plus, and again I will put it in, and again I keep I, and again I made this cyclic permutation L, M, K. So let's put it in just in yellow, just to to show what we are doing. And even I can do like this. So it means that this go in the front, this go in the front. And finally, if we will consider the sum, it will be equal 0. Principle is equality, so it's you can put like this even. So it also can be seen very easily if we consider again this this expression. Okay, so
and that's works for any three indexes, or only when we
yes,
use
any. For example, and you can prove it. For example, I can also write the different way. Let's consider again R, I, K, L, M. And after this, I want to choose I, L, M. I will choose these three indexes, I, L, M. So if I will do again cyclic permutation for these three indexes, so I can write K I keep, it will be M I L plus R. K I keep, oh sorry, yes, K I keep, I put L, and here M I. So this is also true. Any three indexes, but you need to be careful because it's fixed here K, the K can be kept in the same place. Let's see when I will write the third one. So let's put it here, A, B, C as an example, you know. So I can choose, here I choose three indexes. I will write here. Here I choose three indexes, K, L, M. Here I choose three indexes, I, L, M. Let's here to write, for example, I, K, M. So again, I will write R, I, K, L, M. And I choose this one. Let's put what we fixed. We fixed L, okay? So, and other three, we will change. Plus R, it will be M, I, L, K, plus R. I will fix it here. Oh, sorry. We fixed the L. So, and I need to write here what I need to write here. I think K,
K, M, L, I.
M, L, I. So, right. So, again, you can prove it just again to using this this expression. Let's put it in frame. So you just you know, and it's the procedure to prove it. It's not complicated because you just need to rename indexes correspondingly to this order of the indexes. So correspondingly to this order of the indexes, you need to also to put the indexes for metric tensor and for the Christoffel symbols, but to be very careful, because as soon as we are working here with such a kind of expression, here you can see it as it's really very important, the order of the indexes. So the fourth I don't understand how it's better to write it in English. Just a second. The fourth rule, this is, okay, I'm not sure that I will write the names in English right, but it's called You can quickly check it on internet. The name of this mathematician. Z it equality, Bianchi equality. I think it should be C, Bianchi equality. So, what Bianchi equality tell us? So it means that, let's check Bianchi, forget, because sometimes it's, you know, okay. Bianchi падало. Okay. Yes, I made a mistake in the, I think, it is. C. Bianchi, yes, it should be H also. Let's write Bianchi like this. Yes, I saw that exactly. I made a mistake. Okay, so Bianchi equality. Oh, it's better if sometimes it's right, equality, but identity. Which is the same principle, but okay, let's write like this. So what tells us Bianchi identity? It means that if we have curvature tensor R, let's put it here, N, I, K, L, and we have sometimes it's called covariant, no, not covariant, sorry. So, and we will put, because there is a second Bianchi identity, it looks like it's sometimes called differential Bianchi identity. We will speak a little bit later about this. So, and we put here covariant derivative M. And if we will choose, okay, we understand that this is what we obtain. This is a tensor of the 5th rank. So you can imagine that the tensor of the 5th rank. Mamma mia, it's really a long business to work with this. But again, I would like to say is that don't be scared, because we will not work with the tensors with the higher ranks. So, but this equality and the second one will be crucial to obtain Einstein equation. So, and what we will do now. So this is also the rule that if we will choose 3 indexes here, these 3 indexes, and we will do cyclic permutation with these 3 indexes, exactly with these 3 indexes, so it will be also equals 0. Let's write it, plus R n, I we fix, we write M K, covariant derivative L, plus R n, I we fixed, here L M, covariant derivative K, in this equals 0. So to prove Bianchi identity, this already not enough to have this expression for the Riemann tensor. Now I will represent the proof of this, and what is interesting that in despite of the situation that we have really the tensor of the 5th rank, we can beautifully to prove this expression very quickly, respectively, not very maybe quickly, but now. So, for example, let's prove it and to see which trick we can use here to prove it. And it's usually using such a kind of trick in general relativity. So why I would like to represent this proof. Okay, so consider the Riemann tensor and IKL, for example, with this indexes. This is mixed expression. And we can write correspondingly to the formula which we obtained before. So this is a structure like this, d gamma by dx minus d gamma by dx. I will put indexes now here, indexes above. Here should be k, and here L, here IL, and here IK. So plus, you can just rewrite looking on the formula which we obtained. Again, here N, here summation index P, and here P, here K, I, L, minus gamma P, L, N, gamma P, I, K. This is corresponding to the formula which we obtained here. Okay. After this, let's do the following trick. So since and we want to understand, we want to find variant derivative. And you know, sometimes people like to use this expression that everything with which we succeeded finally and invented, it's due to the fact that we are lazy. So of course we are lazy, and for example, I don't like to work sometimes with a very huge long formula because you know you can make a mistake like this, but sometimes we need to do it. Of course, you can understand that it really can be complicated if we will take this expression and after this to consider covariant derivative of this expression. But the trick is the following: due to we are lazy, but not only, we invent something which help us sometimes to build the beautiful theory, and beauty of the theory sometimes is in the fact that it's not can describe which is important the reality, but also because this series is enough elegant, mathematically elegant, and when you coincide together from one point the possibility to describe reality with a high precise, and from another side to write mathematically beautiful theory, so it means that we really succeeded. Because it's a little bit philosophy, because you understand that we can describe reality possibly by different ways. And a bright example, this is, for example, Ptolemy's system which describes the motion of the planet, which finally became very, very complicated with the difference, with the epicycles and like this. From another point, we know that if we will describe everything using Copernicus system, it's also some representation of the world, but mathematically it became much more simple, especially when we go to Kepler world, when we understand that planets move not on the circles but on the ellipses. So, and mathematically it became really much more simple. And this trick we are using all time. So when you would like to build your theory, I would like to say, you, of course, the first goal, this is describes reality. And if you succeed, if you are perfect, so you can even, and the second, to predict something which can be proved later or observed later. The second point, this is to build a mathematically beautiful theory. Why it's important? Because in this case, using the language, mathematical language, you can speak with the nature. I would like to say like this: speak with the nature, and maybe nature can tell you some secrets, and sense that you can find, due to this mathematically beautiful theory, you can find some physical properties of the reality. So this is some philosophical review. Before I will do this trick, which is also, from my point of view, this is beauty of general relativity. So what general relativity and which is our goal? Again, we want to generalize behavior of the nature. I can say like this, and the law of the nature in any reference system and any coordinate system. This is a crucial word of general relativity. So general, it means for any coordinate system. It means, again, as we discussed before, it means that the nature laws should be worked not only in inertial, for example, reference system, but also in any arbitrary systems. But of course, in inertial too. So it should be working in a curved space and flat space, in Galilean system, or in non-inertial system like this. This is the first point. The second point, that we write, and we want to write finally everything in tensor form. And why? Exactly because of the first rule which we would like to apply. To write in the tensor form, it means that tensors allow us really to satisfy this request that equation in one coordinate system will work also in another coordinate system. Okay, so why we will love tensors from the point of general relativity. And now I will make again this trick. We already used it once before, and now I will repeat it such a way that I say, okay, so this is tensor, and it means that the same should work in as we say, in local geodesic reference system or local geodesic coordinate system. It means when we are in Cartesian system, for example. So it means that it's also, but in a Cartesian reference system, we know that it will look like this. So this is just a normal particular derivative, partial derivative. Okay, so, and we just can say, look, let's go to flat space, okay, or let's go from the mathematical point of view, and geometrical, we can say much more precise. We will go to Cartesian's reference, Cartesian coordinate system. In this case, we can put, instead of covariant derivative, it will be like this, because automatically Christoffel symbols will equal 0. But this really reduce the number of summands, because now we can write that in this case A, K, L, M. So I will right here. So we, from this point of view, we go to local geodesic. Sometimes it's coordinate system or Galilean coordinate system or Cartesian. This is the same in principle. So we
However,
Sorry?
maybe in flat in Cartesian coordinate system, this tensor is equal to 0. No, so all Christoffel symbols are equal
But,
to 0
we will
in
look
flat
now.
coordinate symbol
Yeah, we will look
systems.
now. So it looks like it should be 0, but it's not like this. We need to be careful with this. And now I exactly want to write. So in the first, we needed to let's consider what will be the just normal derivative from curvature tensor. Okay, and you will see. So this we need to just take a normal derivative from each term. I need to write gamma LA. So dxk dxm minus d again to here gamma ik. It will be not 0. And you will see why. Plus gamma pkn, and I need put here the gamma pil d xm plus, and I apply to the second summand gamma gamma pil d gamma n pk minus dxm minus, and I'm lazy to continue, so you can finalize by yourself. You just apply the derivative. So okay, the derivative for this last term. So now we will look on this, and yes, as you remarked, this is right, that in this Cartesian coordinate system, all Christoffel symbols equal 0. Why we like to use this system? So they are 0. This is 0. So this will be 0. This will be 0. By the way, this also will be 0 due to this fact. But it doesn't mean that if the Christoffel symbols are 0, the derivative of Christoffel symbols will be 0. This is the point. So, and finally, we need to keep these two summands, which we have. So it means that in a geodesic reference system, so in local geodesic or Cartesian reference system, we will have, I will rewrite it because it will be for me useful. Sorry. NIK divide dxl dxm. So this what we have in the case when we are in Cartesian reference system. If we now will do, and this is a general rule, so it's you can check it in just in mathematical analysis. So if we will do now the cyclic permutation which we need to make, so it means what we said before. We said that if we will change this order, we will obtain identity. So now I want to choose these three indexes, and now I will change it. So I will write Rn, I fixed, M, K, derivative L. So in this case, I will have what I will have. I will write D comma N, and here I need to write. So instead of I keep, instead of L, I need to write K, and instead of K, I need to write, will be the M, the XL, minus D to gamma N, I M, dxk, dxl. And again, I choose these three indexes, and I again will do cyclic permutation. So it will be L, M, K equal. So D to gamma N. And here I need to put below I again. Instead of K, I need to put M. Here, instead M, I need to put so like this, minus D to gamma ILM, dxm, dxk. Let's check. So LM, here KL, here MK. Yes, it looks right. Here KM, here ML, here MK. Okay. And now we need to consider the sum of all of this. So what we will have? Let's the first one, this one, the xk, the xm. So this is exactly what this one. So this will disappear. The second one, which is this one, this is exactly as this one with a, of course, sign. So it will also disappear. And the third one also the same. So finally we have really zero. So we prove it. And it's understandable that since we are working in tensor, I can write here point, and this, sorry, and this will be the same. So the same, and it's better to write maybe in your conspect that since we have tensor character, or tensor properties of this equality, oops, of this identity, let's put it. So this is, this identity is working in any reference system, any coordinate system. So if we put just derivative, or if we put covariant derivative. So this is a trick which is using sometimes to prove some important things, or not to prove some things which you know you are lazy to prove. Of course, you can do everything, and you can be very careful and consider exactly this derivative, to write everything, and finally to discover that this is really equal zero with this cyclic permutation. So, but you can make this beautiful trick to go to Cartesian reference system and to show that it's working there, but it means due to the tensor character of the object which we consider, so it will be identity also in another coordinate system. So this is the main properties of Riemann tensor. We don't have equations, so an equation now we will speak about the next important object, which will be finally in Einstein equation. Okay, in this case, again, I'm not sure in the name, so I will check it now. Oh, right. Yes, that's exactly what I thought. Okay, now we will speak about Ricci tensor. It's just very quickly we will consider it, because you will see that this is really simple if you already know what is a curvature tensor. So Ricci tensor, to find the Ricci tensor, we need to look on the properties of the Riemann tensor. So what we know, that that due to the properties of the Riemann tensor, so if we have a Riemann tensor, this one, and if we make a swapping with the first two indexes, okay, these two indexes, and if we will do so, to make a swapping with these two indexes, so in this case LM, this is summation index, it will be equal 0. You can check it, so, but this is like this. Again, you can look the expressions through the metric tensor. Otherwise, so now you know what is the goal. We want to look, we would like to see what it will be, which object we will obtain if we make this operation of swapping, sверtka, call it sверtka in our language, which we will obtain finally. Finally, as you understand, we will obtain the tensor of the second rank. Consider the swapping by 1 and the third index, and 2 and the fourth. So what it means, this is the first, the second. If we will take again the Riemann tensor, and I will choose the first and the third one indexes. So, and I will multiply on corresponding metric tensor with indexes IL. So what I can see, I know from the properties of tensor Riemann that if it's a symmetric, it's anti-symmetric relative to permutation inside of the pair of the index. So if I change these indexes and these indexes, I will obtain the following. R KIML. Okay, I change here and I change here. So, and it will be the same. We are now consider, because, you know, we have a tensor of the fourth rank. So we have 4 indexes. And now the question which we would like to ask, if we will consider the swapping, so we kill, you know, two indexes from all of the 4 indexes due to the applying of the rule, due to multiplying on the metric tensor, which object we finally obtain? 1, 2, 3, because, you know, it can be different combination of this. And now we investigate it. So again, but we can see that due to the, due to the asymmetric property of the Riemann tensor relative to the change of the indexes, I just play with the indexes. I can write like this. So, you know, I just change the places of the indexes to understand. So I will obtain something different or not. You can see that in any case, up to the sign in front of the Riemann tensor, we will obtain or the 0 as here, or we will obtain the same tensor. So I can write here IKLM equal minus GIL. So I made, you know, some different permutation of the indexes, and I can see, and this is the conclusion of this procedure, that with accuracy of the sign, we can create unique tensor of the second rank from the Riemann tensor. Okay, this is conclusion. That due to the properties of Riemann tensor, curvature tensor, we can create with this swapping a unique tensor of the second rank. And usually we like something unique. So finally we understand that finally we can obtain unique tensor which is not 0. Others combination will be 0, and it's not interesting for us. And this exactly called Ricci tensor. So let's write like this: Ricci tensor. We can write now that Ricci tensor, it means that if we will take the Riemann tensor, KIM, and swapping or sверtka, okay, it means that instead of n here as a top index, we put also I. Or which is the same, not the same, but we can write GIL, RIKLM. It means that if we have a tensor Riemann, and finally, you know, we obtain the tensor of the second rank. And this is exactly Riemann or Ricci tensor. So let's put it here. RKM is called Ricci tensor. So the Ricci tensor, this is tensor which we can create using Riemann tensor with a swapping with first and the third indexes. So we understand that we, as we can see here, we can do some different procedure, but let's consider and let's put a definition that Ricci tensor, this is tensor which we can make by swapping on the first and the third indexes. So this is also we consider as the first and this is third. Okay, and we put the same indexes which tell us that we put a summation index finally to obtain the second rank tensor. This second rank tensor is very important because exactly this tensor will be in Einstein equation. And Einstein needed, and he was looking for the tensor, and we will see, you know, such a, we will go a little bit with the way which Einstein used to find the equation of gravity, because he understood that he understood here, of course, that he has a Riemann tensor which describes the curvature, can describe the curvature of the space, but for it is not how call it, the curvature tensor is not useful for equation of gravity. And you will understand why, because this is tensor of the false rank, but we need exactly the tensor of the second rank. And why? Because from another side, when we will put the matter, some object we describe this matter, and this object exactly the tensor of the second rank, which is a energy impulse tensor. So this is why we need to have this object. Again, and we can write the formula, which is important also with us, for us. Km, and we can write the formula through the Christoffel symbols. For us, it will be much more convenient to work the following problems through the Christoffel symbols. And just the point that in this formula which we have for this one, okay, I'll put it here, this one. So you just need to change indexes, it's all. So if you will change indexes correspondingly to these rules, we will have d gamma. Maybe the summation index will be different, doesn't matter, because as we understand, the summation indexes should be changed with annotation xi minus d gamma I ki dxm plus gamma kmp, gamma here summation index we put here, and here also summation index minus gamma kp gamma p, here summation index, p summation index also, and here mn. So this we can put in frame because so this is expression for the through the Christoffel symbols of Ricci tensor. It also can be proven that due to the fact that Christoffel symbols are symmetrical with respect to the change of the indexes below, the same will be for Ricci tensor. So the important property is that Rkm equal Rmk. And it also can be seen as that this is like this from the expression before. So because you know, if you will look on each summand, it means that it doesn't change. It's only the business of change the order, which is not crucial. And the last important object which we need to describe all this business with the curvature of space, to describe curvature of space, this is scalar curvature. Let's put it here. Ricci tensor here. Scalar curvature. So what is a scalar curvature? It's understandable even from definition. Say put scalar curvature. It means that this is scalar value. This is some scalar which has an information about some properties of the space. And we can obtain it a very simple way. So it means that we need to make a swapping with a swapping of Ricci tensor. So it means that if you have R Km, and you will apply on G Km, so K and M in this case is became summation index, you will obtain scalar. So or also I can, taking into account this one, I can write like this GKM, but instead of RKM, I can write it as I wrote before. So this GIL RIKLM. So I made a swapping 2 times. The first time with this, with IL, the first one, and the same, and the second time with K and M. Okay. So let's put it in frame also. So this is scalar curvature, which is also will be finally in a equation of gravity. I also would like to say that now is a very, we have a really century or time to discover black holes, supermassive black holes, gravitational waves, and so on. It's it's a beginning of this era when we will deeply investigate the strong gravitational field due to technology which we have now, and technology which continue to develop now. So there is a huge project. I will speak later about this with ground interferometers to looking for gravitational waves from astrophysical objects. This is a space interferometers which, as we hope, will be finally built. So this is a lot of things to try to understand what's happened around this incredible object as a black holes, to check is the general relativity is really working everywhere, or maybe, as sometimes before we needed to change Newtonian mechanics with general relativity, or maybe we will need to change something. So for now, we understand that everything is working well in general relativity, but we have also some things which we can't explain for now, and it's also make sense sometimes to consider something alternative like this. So this is really important things. And I just want to say that you will look on YouTube, in the internet, many things, beautiful video discovery, the channel discovery like this. But what is important to understand how you can obtain these things. And of course, now we are exactly doing the point in such a way that, as I hope, if you will follow in all of this, you will understand how general relativity appear, and this all this what we not, of course, we can't, we don't have enough a lot of time to, for example, to investigate other things, but this is really the ground which is important to jump in any field of gravity, including gravitational waves, black holes, and so on. So it was some little philosophical, again, discussion, but in principle, what we need to for the we already have the objects, mathematical objects, which we geometrical objects, let me say, which we need to for the Einstein equation, which can describe the properties of space-time. Okay, so this is Riemann tensor, this is Ricci tensor, this is scalar curvature, this is, of course, Christoffel symbols, which is inside, this is covariant derivative. So this is all this luggage which we need to use it to construct the parts which are related with the gravity, with the curve of the space. Another part, this is, of course, to put the matter, because matter make a space curve, and curvature say to matter how to move, and like this. We will do it, but in the first, just to be a little bit common with this object, I would like to consider some, we have 10 minutes, consider some examples to find or to obtain the components of Riemann tensor and some simple example, and Ricci tensor. Also, I would like to say that up to the multiplier 1.5, the scalar curvature correspond to Gauss curvature, because I all time forget where I need to put 1.5, but it looks like Gauss curvature, which call so it's letter K, and we used it maybe before. Okay, I think it should be like this. This is scalar curvature divided on 2, like this. So Gauss curvature we're also using for describing all the curvature of the surface. So, and scalar curvature correspond to the Gauss curvature due to this factor. Now let's consider examples. One example, and again, maybe I will give you some home task. Example, and you will after this you can play with examples which you would like to look. So let's consider sphere. Sphere. Okay, sphere with the radius which is constant. Let's put it constant. So we would like to consider the spherical surface. Okay, so again we consider two-dimensional space. Why? Because it's much more simple. Not simple and not so long to write. So if we will let's consider theta as a polar angle, so phi, this is azimuthal angle, and we can write the element, the square of the element of the surface, dl square, which, you know, the element of interval in this case is equal to dl square. It will be, since r equal constant, so we will not have dl square, so we have r square. It is r square sinus square theta d phi square. So you can obtain it again simply way just to consider the transformation through the Cartesian system to spherical system. So, and again, if you would like to find some things which are related with the Christoffel symbol, so curvature tensor, we need in the first to put what is x1. So this is theta, x2, this is phi. Okay, we have two coordinates, two-dimensional space. It means that that we have a component of metric tensor, which one? R square sinus square theta. So this one, this is 0, 0. And if you and you know the goal which we can put here to obtain the scalar. So I want that we will find IKLM components, also component of Ricci tensor, and scalar curvature. I will start, and I want that you will finish it at home as a home task. So I will show you an idea. Maybe we will finish quickly, I don't know. So let's consider, for example, and understandable that scalar curvature, it's only one component because it's a scalar. Okay, so let's consider, for example, this term. And also we understand that, for example, for that it should be a lot of components of Riemann tensor, for example, but of course for two-dimensional space, it will be much less. For example, for four-dimensional space, for the space and time, independent should be 20 components, if I remember correctly. But if, as you will see again, you will understand why finally a lot of components reduced, for example, when we are working with our universe, to build the model of the universe. So, and you will understand why we have like this. In this two-dimensional space, we have also just a few principles. This is two non-zero components. So, and we just, to obtain it, we just need to put here, instead of the index, instead of the K and M corresponding summation, we need to put numbers. Okay, so I will look on this. Okay, so I just need to write d gamma 2 to 1 divide on the x1 minus d gamma. I will use the numbers, not the letters. So 1 x2, okay, plus gamma minus gamma. And looking again here, look on this, I need to put here not here, I need to look here, this one. So this one, okay. Yes. So here it will be P, and after this we need to put this in this one, 1, and this one and this one, 2, 2. Here we need to put again indexes It's in summation index. And here we need to put 1, and here 1. So, and as you understand, this is only the point one to have all Christoffel symbols. So the procedure is such a way that in the first you need to calculate all Christoffel symbols to understand which are of them are 0, which are not 0. So I will not do it. Again, for your home task, you need to write everything much more careful. I just want to say that so this will be equal to 0 due to the fact that and the symbols will not be. This sum and will this one, it will be also 0 because Christoffel symbols gamma 1 1 1 equal gamma 1 2 1 equals 0 in this case, so it will be 0. And finally, consider of this, so we will have only d gamma 2 to 1 dx1, but we have also, and here we should be careful with this point, because here we have a summation index p and p. Okay, p is here summation index. It means that we need to write gamma. Oh, I forget here to write the indexes. Which indexes should be here?
2.
Yes. So I need to write 1 to 1 gamma 1. Okay, so instead of p, p equal 1 and 2 in this case. So minus, and now instead of p, I put 2 gamma 2 to 1. And again, I just to look what is a 0 and what is not 0. So since we will prove it is equal 0, so it's understandable that it's equal 0. So finally, I will have only to summand for this, and you will find it at home. You can very quickly to show that gamma 2 to 1, if you will obtain it due to the formula,
So 1 divided by 2, 1 divided by, or we can result or the weight.
yes,
the result.
can you tell me result for gamma 2 to 1?
Result, no, it's
Yes, we need to
must be
time.
calculated. Okay, but
yeah, we can just, you can see that we already don't have a time for this. So I will give you as a, let's try to do it as a home task. So no, not let's say home task, and we will finalize it on the Monday very quickly. Home task, please find all gamma for this metric. Okay, and after this we yes.
Okay, no, I already found the result for this gamma.
Okay, but since we,
okay.
I would like also, but with whom I speak, because you know I don't with whom I speak now.
Kononenko, Semen.
Semen. It's fine, but I also would like that everybody will, and I will take into account again for the final mark when you will give an exam. Please, and this is additional procedure to work. Please find all Christoffel symbols for this metric using the expression for Christoffel symbols through the metric tensor, okay, which we received before. After this, in the beginning of the next lecture, we will very quickly to finalize, to obtain a component of the Riemann tensor for this metric and scalar curvature. And I will give you, and we will start already to work, and we will work with the second identity of Bianchi, which is crucial for Einstein equation because it's really the left part of the Einstein equation. And I will give you a home task to obtain something for to obtain the Riemann tensor and the scalar curvature, maybe for some metric. So this is an idea. If you don't have any questions, now I will make a screenshot of some questions.
Yes, I have some question. On last lesson, you promised that you will show us correct solution for first home task.
Yes, look, I have my formulas writing by hand, so I can make a copy and send it and post it in my page, and you can look on this, because otherwise we need.
No, or you can just send the photo of these pages into our Telegram group.
Okay, and I will decide how I will put it, or in my page with a link, and everybody can go and during some times to download it or immediately to. Okay, so and you can see it very. Yes, I promised I will do. Don't worry. Today I will do it. Okay. In principle, I can do it even now. Okay, put it in Telegram chat. Okay. All right, I see it. Okay, so first. It's enough to pages. So, okay, just now I will send you, wait. This is the two derivative which you can obtain, as for covariant and contravariant case, and also to represent that for this both case, the expression which you obtain, the second summand, it will be changed, it will be difference with the sign. Okay, Cosmology. You can see it now. Can you see it? Can you hear me?
Yes, we see it and we can hear.
Look, and then the end, there's 13 formula. You can see it.
Mm-hmm.
So the first maybe the indexes are different, doesn't matter. So the first you can see in principle the beginning how we can obtain covariant derivative for the covariant vector, and after this we obtain expression for covariant vector, which is here 8. You know, now we are doing everything in order because we are writing now a book about general relativity, and exactly. So if you will find something wrong, please tell me. And after this, we do this. So this is the opposite side which I gave to you. So in the first, this is covariant, and the after contravariant. And you can see the differences because the crucial here is this formula 13. So you can see why really we have a different sign for the formula for the covariant and contravariant derivative. For the covariant derivative of covariant and contravariant vector. So it's understandable for now.
Maybe yes.
No, I just need to follow this, to repeat it, and you will understand, I hope. So the crucial, again, the formula 13. So, and you can see why on the left you have a minus, and the right side you have a plus. So, but now here everything should be clear. Okay. So if you made some mistake before, you can check now. This already I checked. It should be everything right, but we didn't do any mistake as I remember. Okay, if you don't have any questions, so now you know which is your home task. Again, I will fix all home tasks. Please, for this time, please send me before Monday, or the limited, for example, Friday. But please send before Monday, because we will need it. So you will need to understand what we will substitute on Monday when we will work with the Riemann tensor. So some other questions? No? Okay, in this case.
Вибачте, я українською. Мої домашні завдання до вас доходять? Я на
Андрей,
пошту надсилаю. Денис
Федоренко. For example, last one I can see this is Sergei Popkov, Denis Fedonenko, Alexander Kramyuk, Yaroshenko Andrei. Yes, you speak now with me. Because I don't see you.
Доходять до вас, да?
No, I don't see you. No.
Ні, ну от.
Are you sure that you are using Dima Odinets I have? But I don't see in my post Yaroshenko Andrei for now.
So what about me? I sent you my last home task yesterday near 8 hours.
Семен Kononenko, see.
Okay.
Yes. I said Семен Kononenko, see Храмук Alexander, Denis Fedonenko, Sergei Popkov. This is last one which I received before. I will make Dmitry Odinetsky. I will make a special file. I have already, but I will put everything inside to calculate the number of marks which you have reached. But again, Stanislav Tokarsky I have. But again, Katerina Солов'ян, Семен Kononenko, this is previous, Храмюк Alexander. But again, please take into account that somebody who will send me all of the tasks before exam, I will not take into account this. It will be like one or two marks, and it's all. So please send me in time, because it's understandable that after this, in the end, you can take all the solution from your friends and to rewrite everything and send to me. So please don't do it. Again, I give a limit up to which time you can send me this task. The previous task up to Monday. So I give for all tasks 1 week. Okay, this is the point. Okay, if we don't have, so I unfortunately, unfortunately, I didn't receive. Andrei Yaroshenko, see? You asked me. Who asked me?
Yes,
I didn't receive your, again, I write my email here, so please check it. I use,
Ні, я от іменно, може мене в спам кидає, я не знаю, я можу в телеграмі, на телеграм надіслати листи, ну, як я і надсилав.
write me,
Продублировать.
please, on this, my post. Which is, I also check. This is my work post. Enough it. Italian National Astrophysical Institute. So you can try to send me on this address, but for me it's better to if you will send me on this one. Horizon I don't check because it's already I have a, it's not convenient for me. Okay, so
Okay.
So this
Remember,
is-
can you
this
check?
is-
Can you check spam because it can?
this, please use this one. This is just spam. Okay, I will check later. Okay, my spam. What try to find. If I will not find, so I am Andrei Yaroshenko. Yes, right.
Yes.
Okay, Andrei. Okay.
Thank you.
Okay, so see you on Monday. Good weekends.